Lesson on technical sciences. We are still continuing with momentum and impulse, and we are actually doing quite well in this topic because we have been able actually throughout the week to look into questions that are really from low order as well as high order questions. So I'm really expecting you to be doing well. So again, I hope you have your pens, your paper ready, as well as your calculators, and then we will be able to continue. Now, as promised from yesterday, I wanted us to look at also, a variety of questions in terms of how we can actually ask you to perform your calculations in terms of momentum and impulse. And today we'll still be focusing on impulse, and we'll still be focusing on really applying the principle of conservation of linear momentum. Now, when we are done, then I am expecting tomorrow that we will be concluding this particular topic in terms of questions from previous examination papers as well, so that you see how we ask and also how these particular questions are marked. So let us just go through the lesson and enjoy it. Again, I will just be reminding you what you need to know as per the examination guidelines, but briefly so. But more on today's topic will be just a focus on questions and things that I want you to be able to pick up in various questions. And we will be answering questions on momentum and impulse. And lastly, we'll just be reminding those that are new for today how many marks this topic is going to be at the end. So basically for the overview part, remember you have your examination guidelines, my dear learners. And in the examination guidelines, there are definitions under this topic. So I'm expecting that you will only be using your examination guidelines to give definitions for this particular topic. And also the principle here, which is the principle of conservation of linear momentum. This is a principle that you get in your examination guidelines, and you must state it as it is in the examination guidelines. So please be able to use that. So I want us to look at this question for today and see how best we can analyze this particular question as well as answer the questions related to it. Now, they tell us William drops a rubber ball, mass 1,0 kilograms, vertically downwards. It hits the floor and bounces back. Now, the graph represents the average net force the ball exerts on the floor as a function, right, of time. Now, if you check here, what is happening before we even go to the graph? Okay, my pen is stuck here. Right? Sorry about that. Let us continue. So, William is dropping a ball, and this ball has a mass of 1 kilogram. So it goes down, and it is, as it is moving, it moves with a velocity of 4 meters per second somewhere on its journey, but it has been dropped and it is going vertically downwards. So when it reaches the floor, my dear learners, what you should be able to pick up there is that the ball will exert the force on the floor, and the floor will most definitely exert a force on the ball. And that we know according to Newton's third law of motion. So the graph that we've been given here is a graph that gives us the average net force. We can see the net force here measured in newtons, and then there we can see the time. Now, basically what I see here is that I'm having a relationship of the net force that is acting on the object as a function of time. So basically, this is the average net force that the ball exerts on the floor, but we also know that this is the average net force that the floor exerts on the ball. And based on this particular graph, we can definitely see that this net force is acting on the ball for a period of 0.1 second, or it is acting on the floor for a period of 0.1 seconds. So if we know the net force acting on the object and the time the net force acts on the object, it means we can actually calculate what we refer to as impulse. You will remember again, my dear learners, that when we talk about impulse, we are talking about the product of the net force acting on the object and the time the net force acts on the object. Now, let us look at some of the questions that we can actually ask you. Now, for question 3.9.1, we are asking you, what physical quantity is represented by the area under the graph? Now, if we want the area that is given under the graph, then we go and check. The area under the graph is this area here altogether. And this is definitely a triangle, as you can see it. And the area of a triangle, it have the base multiplied by the height. In other words, it is half the base multiplied by the height. Now the base is the time, and this is the time that the net force is acting, and the height is the net force, or what is referred to here as the average net force. So if I get the half the base multiplied by the height, basically I'm getting a product of the net force acting on the object and the time the net force acts on the object. In other words, that product there, which is the area under this graph, definitely represents the impulse. And that is what impulse is, definitely by definition. Then we are required to calculate the change in the momentum of the ball. Now, some of you learners, you might actually think that this question is difficult, but it's actually not, because by definition, you know, or from a formula, we know that F net delta T is equal to delta P. So if you want the change in momentum, we actually know that the change in momentum is actually equal to the impulse, because this represents the impulse and this represents the change in momentum. In other words, from this graph, if I want to calculate the change in momentum, I can actually calculate what? The impulse that is acting on the floor, or the impulse that is acting on the ball. So we actually do not need any other information other than that. Now, impulse is the area under the graph. And if it is the area under the graph, we can see that the area under the graph is given by that shape, which is the shape of a triangle. And we know the area of a triangle is given by half multiplied by the base and multiplied by the height. So the area there will then be half multiplied by the base, which was 0,1, the contact time, multiplied by the height, which is 140 newtons. And then we find that our impulse will give us 7 kilograms dot meter per second upwards. And our answer is positive altogether. Now, why are we saying the direction is upwards? Because when the ball hits the floor, then the force that acts on the ball is an upward force. But the force that the ball exerts on the floor is definitely a downward force. So there we are getting 7 kilograms dot meter per second. And we were asked to calculate the change in the momentum of the ball. So, you know, to always be on the same side, you can just say, therefore, change in momentum, it's exactly equal to 7 kilograms dot meter per second altogether, just for you to be able to show them the change in momentum. But what you will do is you will be getting the impulse first. After getting the impulse, then you tell us that the impulse is actually equal to the change in momentum, and this gives you 7 kilograms dot meter per second upwards. Why are we giving direction, my dear learners? We have to give direction because we've been asked for the change in momentum, and the change in momentum is a vector quantity, and therefore we must give both magnitude and direction altogether. Then they tell us if the speed with which the ball hits the floor is 4 meters per second, calculate the speed with which it moves upwards and away from the floor immediately after the collision. Now, what do we know, my dear learners? We definitely know that after it hits the floor, because remember it was dropped, right? It was dropped. Then they tell us that when it hits the floor, it hits the floor with a velocity of 4 meters per second. So that is when it hits the floor. Now we want to know what is the velocity with which it moves upwards. Now, my dear learners, obviously when it moves upwards, then we know that the velocity is going to change. The velocity with which it hit the floor is not the same velocity with which it leaves the floor to go upwards altogether, right? Now, to calculate that, it's quite easy. We'll still use that formula for impulse, and we will say F net delta T is equal to delta P. Now, from 3.9.2, we have actually calculated that impulse altogether. So we won't need to calculate impulse again. Then we know that change in momentum is actually mvf minus mvi. Then the impulse, we know that it is 7 kilograms dot meter per second is equal to the mass was 1 kilogram. Then we want the speed with which it leaves the ground. So that will be V because we don't know its value. Minus then the mass of the ball, it's still 1 kilograms, and the initial velocity of the ball is 4 meters per second, negative. One negative because we chose upwards as positive. So when it was hitting the ground, it was actually going downwards. And then we see that V is actually 3 meters per second upwards. Why are we saying upwards? Because the velocity there is positive. And once we get the velocity that is positive, based on how we chose the direction, then we can definitely see that it is definitely going upwards altogether. So we'll actually get a mark there. We'll get a mark there. Then for the entire substitution being correct, we will get another mark. Then we will get another mark there. It could be 2 marks, a mark for both the magnitude as well as another mark for direction, or a mark that is just a single mark for both the magnitude as well as the direction. And that is why I always tell you, it is important for you to actually read your question thoroughly, because there, you know, if it was velocity, then the direction is actually important. But for this one, because they said the speed, even if you don't give us direction, then we will still give you a mark. Why? Because when you talk about speed, we are talking about a scalar quantity, so you don't give direction. But if it was velocity, then you will definitely give us direction. Right. Now, I want us to interrogate some of the questions here. And they ask us, which one, and these are multiple choice questions, and you must be able to work with these altogether. And you must be able to apply the elimination method. In other words, eliminating answers that are completely wrong, and you are likely to be left with 2 answers, and you will always have the most correct answer, which is the only answer that is correct. So they ask us, which one of the following units is not the correct unit for impulse? Now, a unit that is not correct here, number 1, let us check for those that are correct. Now, impulse is the product of the net force acting on the object and the time the net force acts on the object. So, F net delta T by formula will give us that it is equal to delta P. So we know this is impulse. So impulse, it means the SI units for impulse, which are the actual SI units, is that you will be multiplying force, which is measured in newtons, and you will be multiplying with the time because you are getting the product, so which is seconds. In other words, the SI unit of impulse, it's Newton second. So the first one is actually correct. Then let us examine the second one. The second one, we can see that it is actually equal to the change in momentum. And we know that the change in momentum is measured in kilograms dot meter per second. So it means the second unit is also correct. Then the third unit, we definitely know that it is incorrect. Why? Why is it incorrect? Because we know the SI unit must be Newton second and not Newton per second. Then you go to D, kilograms dot meter per second. So remember, the stroke there means the second, it's still a denominator. So if you brought it upward, it would be second exponent -1. So the unit for B and D, it's actually the same. Are we together? Now, let us go to question number 2. For question number 2, my dear learners, what you should be able to see, let me just erase there for you. What you should be able to pick up there is that They are asking us which one of the following units is the correct one for momentum. Now, if we want the correct one for momentum, we want the SI unit for momentum. And by now, we know this is a recall question. So the unit for momentum which is correct, it's actually that one, which is B, right? I just put it incorrectly there for you. The correct answer there must be a B, because we know momentum is measured in kilograms dot meter per second, right? Then they ask us, a truck is driving at a certain velocity on a road. A car with half the mass of the truck moves twice as fast. If the momentum of the truck is P, what is the momentum of the car? Now, what is happening here? They are telling us a driver is driving at a certain velocity on a road. So now we have a car, but the car actually has half the mass of the truck, but it is moving twice as fast. Now, if the momentum of the truck is P, what is the momentum of the car? Now, to put it simply there for you, my dear learners, P is equal to mv, right? And they tell us the momentum, let us talk about this one. Let us say this is the truck. Right? If this is the truck, then they are telling us that its momentum, which is the momentum of the truck, is P. And we can take P to actually be equal to mv. Then what is the momentum of the car? Then to check the momentum of the car, we go again, we say car P is going to be equal to mv. Now, they are telling us that the car has half the mass of the truck. So it has half of that, which is half of m multiplied by, but now they're telling us it is moving twice as fast. It means its velocity is 2 times that one. In other words, it is 2v. So if you do your mathematics, half of m multiplied by 2v is definitely going to give you mv. So what you can see is that both the momentum of the truck is P given as mv, and the momentum of the car, it's still P is equal to mv, and you still get mv because the mass is half that of the truck, but the velocity is twice of that. In other words, the correct answer there must be a B altogether. Right, so this is some of the questions, and most of the time the type of questions that you will be getting in your multiple choice questions, and I'm really urging you to perform in these type of questions. Now they ask us, a cricket ball, mass M, falls vertically downwards and hits the ground with a speed of 2v. It bounces back with a speed of v. What is the magnitude of the change in momentum of the ball? So how do we answer that one? You can just go to your formula and say delta P is equal to mvf minus mvi. Now, let us say downwards is positive. In other words, upwards is going to be negative. So the change in momentum will be given by the mass is given as m and it falls vertically downwards, and it hits the ground with a speed of 2v. So this one, it's actually the initial velocity, because we check when it was bouncing and then when it was basically hitting the ground, and then they tell us it bounces back with a speed of v. So that one will then represent the final velocity. Why? Because we are actually focused in the change in momentum right when it was hitting the ground and just when it was leaving the ground and bouncing back. So the final velocity then is Vf, and our Vf is going to be negative V. Why negative V? Because then it is bouncing, so it is going upwards. Minus the mass, it's still m, but the initial velocity. Right? The mass is still m, but the initial velocity is that one, it's 2v when it was hitting the ground, and that's when it was going upwards. So in other words, it's positive 2v. That's when it was going downwards. Then you do your mathematics. M times negative v, it's negative mv. Negative m times 2v, it's negative 2mv. So negative mv minus 2mv, it's going to give me negative 3mv. In other words, the magnitude is then 3mv, and hence our answer that is correct there, it must be a D. Then we move to the next question. They tell us a ball of mass 0.2 kilograms hits the ground with a vertically downward velocity of 10 meters per second. It bounces back with a velocity of 5 meters per second. The impulse of the ball on the ground is, so we are supposed to get the impulse here. Now, what is the best thing to do there, my dear learners, is to say, let me check and try to calculate it. Now, to calculate it, you will say the formula for impulse is F net delta T is actually equal to delta P. Now, the product of the net force and the time the net force acts on the object gives me the value for impulse. Then, in other words, F net delta T is equal to mvf. Okay, that one is not nice. Right? It will give you mvf minus mvi. Now, how do you know that it gives you mvf minus mvi? Because when you go to your formula sheet, you will see that there is a formula that says delta P is equal to mvf minus mvi. And I'm just going to work with this side. Why? Because this definitely represents my impulse. Then the mass, it's already in kilograms, so I will definitely substitute it as 0.2 kilograms, no direction. Why? Because it is a scalar quantity. Then let us choose downwards as positive. In other words, if downwards is positive, then upwards is going to be negative. Then the final velocity, that is when it bounces back with a velocity of 5 meters per second. So this represents my VF. And when it bounces back, it means it is going upwards. So there I will substitute 5, but remember it's a vector, so it must be given direction, and upwards is given as negative, minus the mass again, right? That is supposed to be a bracket, right? Get our pen again. The mass is still 0.2, and the initial velocity, that's when it was hitting the ground and it was going downwards. So it's actually a positive 10. Even if you don't indicate the positive, it's fine altogether. Then we check 0.2 multiplied by -5. So you must be having your calculators there. And if I do it, I say 0.2 multiplied by 5, I'm getting a -1 altogether. Right. Then minus 0.2 multiplied by 10, it will definitely give me 3, multiplied by the negative, rather it will give me a 2. Multiplied by the negative, it will give me a -2, and therefore I will have -3 kilograms dot meter per second. And from that, I can definitely interpret and say the negative means upwards. In other words, my impulse must be 3 kilograms dot meter per second. And what does the negative mean? It means upwards. So the answer that I'm going to look for there is definitely C. Right. Why is it C? Because I am definitely getting a negative answer. Right. So that one is just a typo. Right. We can see we are getting 0.2 times -5, it's -1. -0.2 multiplied by +10 is -2. So that gives me -3 kilograms dot meter per second. So that must be 3 kilograms dot meter per second. And according to us, the negative means upwards. Right. Now, let us look into contextual questions. Now, here we have 2 laboratory trolleys, P and Q. They move on a horizontal plane towards each other as indicated in the diagram. So they are going towards each other. So we can see that the other one has a mass of 2 kilograms, moving at 5 meters per second to the right. The other trolley moving at 2 meters per second to the left, having a mass of 1 kilogram. Now, they tell us the 2 trolleys collide head on. And it makes sense because they were moving towards each other and they get stuck to each other. Now, when they get stuck to each other, we definitely know that this collision is a good example of an inelastic collision. So this collision is an inelastic collision. So when they get stuck with each other, we know after the collision, these trolleys are going to move with the same velocity. Then they move further as one. Then they say calculate the velocity with which the 2 trolleys move together as one after the collision. And hence I'm saying the velocity is going to be the same because now they are moving together as one. Then we are choosing to the right as positive. Then we apply the principle of conservation of linear momentum. Now remember what the principle says in words. It says the total linear momentum Rather, the total linear momentum of an isolated system remains constant. Or it says the total linear momentum of an isolated system is conserved. Now, what does that mean? It simply tells me if I want to put it into a formula, the total linear momentum before the collision is definitely equal to the total linear momentum after the collision if the system is isolated. Then we break it down. We know the total linear momentum before means we must sum the momentum of trolley 1 and trolley 2. And the same will apply for after the collision. So the momentum is the product of the mass, the object's mass and its velocity. And hence it is applied for the momentum of all the objects there. Then trolley 1 has a mass of 2 kilograms. There they are. Trolley 1, 2 kilograms, 5 meters per second. 1 kilogram, 2 meters per second. So trolley 1 has a mass of 2 and it has an initial velocity of 5. Why? Because it was moving to the right and we chose the right as positive. Plus the momentum of trolley 2. So the mass was 1 kilogram and the velocity was 2 meters per second, but remember it was going to the left. So if the right is positive, then the left is negative. And this will be equal to, now what you should see here is that this velocity, we take it out as a common factor because it's an inelastic collision. They are moving together as a unit. They are stuck to each other. So if you remove it as a common factor, then you will be left with the mass of trolley 1 plus the mass of trolley 2. Then you perform your calculations, you will see that it will give you a velocity of 2.7 meters per second. And it is a positive value. In other words, the direction must be to the right. So we will get 1 mark there, perhaps 1 mark for the entire substitution, 1 mark there, another mark there, as well as another mark there. Remember, we wanted the velocity, not just the magnitude. So we had to give direction as well altogether. Right, so this is sometimes 5 marks or 6 marks, because if we give it for 6 marks, it means we will also allocate another mark there. Right. Now, let us look at this particular question. Here we have 2 balls, each with mass and velocity as indicated in the diagram, collide head-on. After the collision, the 2 kilogram ball bounces back with a velocity of 2.5 meters per second. So what we see on the diagram there is that before the collision, the initial velocity of the 2 kilogram ball was 2 meters per second, and the initial velocity of the 5 kilogram ball was 3 meters per second. And after the collision, the 2 kilogram, they tell us it moves backwards, right? Meaning back to the original direction. And back to the original direction, it's moving at 2.5 meters per second. In other words, the VF is definitely to the left. Altogether, so make those markings and those extra information, put it there on your diagram so that you are able to check what is happening with your ball. Then we are required to name and state the law applicable to this problem. So the law that is applicable to this problem is the law of conservation of linear momentum. But they didn't just say we must name the law, so you need to read thoroughly. We are also required to state it. And we know that the total linear momentum of an isolated system is conserved in both magnitude and direction. Then we are required to calculate the velocity of the 5-kilogram ball immediately after the collision. Remember, this velocity before the collision was given. So here we are actually required to get the velocity of the 5-kilogram ball, and that must be after the collision. Right, doesn't look so nice, but that is after the collision. So we know the total linear momentum before the collision will be equal to the total linear momentum after the collision. And we are choosing to the right as positive. Then we break down the formula into product of mass and velocity for both of them before, for both of them after. Now, they are separating after the collision, so we are basically dealing with a collision that is elastic. So our collision here is definitely elastic. Right, what does this mean? The total linear momentum before the collision is that after the collision, we break it down into formulae. So the velocities there are going to be separate velocities, right? We won't take out the common factor because the two balls separated after the collision. Then the mass is 2 kilograms and the initial velocity is 3. And it's positive. Why? Because the 2-kilogram ball was going to the right, and to the right is positive. Plus, then we go to the second ball. The mass is 5 kilograms, but the initial velocity is 3 meters per second in the negative direction because initially it was going to the left, right? So that's one mark there. That is another mark there. Then after the collision, this 2-kilogram one has a mass of 2 still, and the velocity after the collision is 2.5 meters per second, but they told us it moves back. It means it went back to the original direction, which is the left, and hence we have a negative there. Plus the mass of the trolley, of the ball after the collision, it's still 5, and the final velocity after the collision we do not know. So we find that the final velocity after the collision is negative 0.8, right? Negative 0.8 meters per second. Then we interpret the negative, in other words, it's 0.8 meters per second, and that will be to the right. So it will be another mark there, as well as another mark. So that is more or less 5 marks altogether. So that brings us to the end of our lesson for today. And I hope that you have really grasped this particular topic. From tomorrow, we will be concluding the question, rather the topic, in terms of dealing with questions from previous examination papers, so that you see very well how we ask you these particular questions and the depth with which we ask you these questions. I hope that you have definitely learned something from today, and I wish you the best again in your revision for this preparatory examination. And just before I forget, remember, if you've just tuned in, 22 marks for this particular topic, so learn it thoroughly. It is a lot of marks. I have enjoyed the lesson. I certainly hope that you have, and I will see you some other time, which is tomorrow, same time, same place. Enjoy the rest of the evening. Goodbye.